Hi everyone. So it's our pleasure today to welcome Jiafan Wang and Sherman Chow from the Chinese University of Hong Kong. Sherman is going to tell us about one of his recent works on multi-writer SSE, and the stage is yours, Sherman. Thank you.
Okay, thank you. Thanks for the invitation. Happy to be here. Haven't been talking about searchable encryption for a while. That is a joint work with my PhD student, Jiafan Wang. He will be graduating soon. So the title is, if I pronounce it correctly, is Omnes Practical Multi-Writer Encrypted Database. So that Latin part should stand for all for one, and hopefully you will see what I mean after this talk. And yeah, just stop me at any time if you have any question. I'm fine with that. So let's get started. So I will go with a very quick introduction. So we are considering an outsourced encrypted database. And for here, I want to establish some terminology. So we have the writer who has a whole bunch of file marked with different keywords like crypto, privacy, safety, etc. So he or she want to upload all these files encrypted to the cloud. And then in that sense, he or she is writing to the cloud. And now, yes, things are encrypted over there. So that is just a simple upload of a whole bunch of file. And now we have another role who is called reader. Reader want to search for something marked with the keyword crypto. So at this scenario, we have F1, F3, and F6 as different file to be retrieved by this reader. Okay, so we have writer and reader, and that is the simple outsourced encrypted database scenario we are talking about. So I hope I set up the context clearly. And now the usual stuff, the definition of a dynamic searchable symmetric encryption or DSSE. So a client can of course write to the database that, or in SSE terminology, we call it update. And of course, the same client can search. And in our new terminology, that's reading from the database. How he or she can do that? So that will be done by a process which delegate the corresponding token, which means either the reading or search token, or writing or the update token to the cloud server, and then the cloud server can execute the corresponding operation accordingly. So that is DSSE. DSSE has a number of nice features, so that is almost like every modern DSSE scheme features sublinear search, within that the search will be the search complexity will be sublinear in the size of the database. And why it is possible is because the writer has indexed the data accordingly. So for example, for here, all these files linked with the keyword crypto are just linked together. So it features sublinear search, which is nice. And another de facto standard for security is for privacy. In a nutshell, that means the search token that being delegated for this moment, that means it will be authorizing the cloud server to do the search at this moment. So yes, I emphasize at this moment. So after this moment, the O token will just lose the function after the search. So for privacy is this requirement. And if you think about that, there's nothing you can really take away from the O token. Revocation is a notorious issue in cryptography. So you do not want the O token to remain authorized to search forever. There's another trick you can do, which is to refresh the database such that you can adjust the database accordingly to indirectly invalidate the O searching token. Okay, so that is our two nice property of DSSE. But yes, I started to talk with a multi-writer scenario that is not applicable to it at all, because writers is simply the reader. They are just the same person. Okay. And on the other hand, of course, we have the multi-writer scheme that is the public key searchable encryption. In this talk, we will call it a PKSE instead of PKESS like keyword search. So PKSE, so multi-writer can use PKSE to jointly contribute to a single reader, just like regular public key encryption, but there is an additional feature which is search and token generation. Because we will be using anonymous identity-based encryption or anonymous IP as a building block, so I will just quickly recap. how PKSE can be built from enormous IBE. The idea is you just treat the identity in IBE as the keyword you want to search in PKSE. So in that sense, that is our usual setup and key generation algorithm, which has one-to-one correspondence with IBE. Encryption is still like the same, but you encrypt a fixed dummy string. And for the token generation in PKSE, that correspond to the private key extraction in IBE. And to test whether a ciphertext is mounted with a certain keyword, we'll try to use this token, aka secret key, to decrypt. If you get back the dummy string, then you conclude that particular ciphertext has the keyword you're interested in. Okay, that is a very quick recap. I hope for this audience, I don't need to spend too much time on this. So I just will skip this. Yes, and now we have the nice feature of private key searchable encryption is, of course, it supports multi-writer, and it supports in the following way. There's no secret distribution at all because there's just private key encryption. Every writer can just use private key to encrypt. There is also no synchronization for the communication in the sense that the writer can just pop up without talking to the reader beforehand and then encrypt under the reader's private key. That is the only information the writer required. So as long as the private key has been retrieved, the writer don't need to wait until the reader to get online, talk to him or her, then start doing this PKSE encryption. So that is the nice aspect of PKSE. But on the other hand, that is very difficult to achieve for security and sublinear search. So as the scheme I quickly reviewed in last slide, that is a test algorithm instead of a search algorithm. You can at best test whether a given ciphertext match a given keyword or not. So in that sense, by definition, you need to go through it one by one. So that's linear search in the size of the database, which is not good. And there is also another requirement which actually affect both security and efficiency. I call it controllable search. There's no controllable search supported, meaning that the reader cannot limit or confine the search scope of a token to just some particular writer. Yes, there can be a trivial approach, but in general, that is not well supported by that. Security-wise, that's obvious because we want to confine the scope of the searching process. For efficiency, yes, there is also talking about efficient property in the sense that you don't need to touch upon part of the database, so that can be more efficient. Imagine you're only interested in one particular writer's ciphertext, why bother to try searching for the other? Okay, so that is the rough status of PKSE. So that's nice for multi-writer, but we don't get the usual security feature from or the efficiency feature from DSSE. Okay, so then, yes, that is a slide I just adopted from some prior searchable encryption work. The focus, at least for that particular talk, would be like talking about the functionality versus security, or in general, efficiency of search operation versus security. So we are still doing something like that, but on the other hand, what is missing from this treatment is we don't have another dimension talking about who are the writer, who are the reader, and we do not have the dimension of a multi-writer. That is sort of being not having too much attention from the literature, and that is the problem we are going to tackle for this talk. So talking about that, there do have a little bit of research on something related. So of course, we still have our first public key searchable encryption by Boyer et al. In Encrypted 2004. So to quickly recap, that is the search capacity is linear in the database size. This little star means each operation is actually a public key or asymmetric operation. There's low privacy, there's low controllable search, I just explained it. That's a proposal from a transition of cloud computing. I made up this acronym. It stands for private PKSE. So there's still a PKSE, so search capacity is still linear, and yes, by the name itself, it achieves some form of for privacy, but still low controllable search. And there's another proposal, I call it SPCHS, which stands for Searchable Public Key Ciphertext with Keyton Structure. That is the name they come up with. So that's appeared in IEEE TIFFs, another journal. So they actually achieve something quite nice in terms of search complexity that is actually sublinear in database size or linear in the number of update on the keyword. That means basically the number of file which that with the interested keyword market. So that is what we want to search for. That's optimal. But yes, this little star here means that every step, including the traversal step, is a public key operation. So yes, that is sublinear, but on the other hand, that is also not as efficient as one might hope for, because there's public key operation. And yes, this proposal is back in 2015. For privacy is not yet formalized, so not for private, not because of each of these controllable search property. Okay, and so that is our status of the research landscape. And so that is not a desirable situation. So of course we are going to tackle that. But before tackle that, let's talk about some of the challenge in a high-level manner. So we have public key searchable encryption, which, as mentioned, does not require secret key distribution, does not require synchronous communication, and those are useful features in scenarios such as for this one, that's a sensor or electronic health record. That's difficult to imagine a daughter carrying a device with him or her with the secret key embedded. That's risky. And sensor, yes, that's still the same story. And on the other hand, for other scenario like email, you do not expect you talk to the reader first and then get some feedback, and then you talk to the reader again to encrypt the email. So that does not make sense. So those will be the nice feature we want to have. But yes, they are also interrelated to some of the other features we want to achieve. For example, DSSE, it does have the sublinear search, it does have FOIA privacy, but on the other hand, reader is simply the writer in this SSE. So by definition, both parties are synchronized because they are the same party, and yes, they are just holding the same secret key. So that's this step. So there's always a trivial solution which will just surrender the secret key of the SSE, but on the other hand, you cannot really differentiate or separate the reading power from the writing power. So that is this trivial solution does not work at all. So you can see now they are sort of interrelated. And then yes, we still did not talk about new property of controllable search. And as mentioned, that's good for efficiency and security. So those will be the challenges. That means we want to achieve all these 5 nice properties simultaneously. And then our answer would be the primitive we are going to formulate, which we call it a hybrid searchable encryption or HSE. You will see in a minute why I call it a hybrid searchable encryption. But yes, that is the introduction part at this moment. Any questions so far? Okay, you can always stop me later. So yes, that is our hybrid searchable encryption. So in another sense, we are trying to see this problem as simple as the typical encryption problem. So in doing public key encryption, you don't just use public key encryption to encrypt the whole entire payload. Crypto 101 teaches you that you want to make the common case fast. You want to encrypt the larger payload with symmetric key encryption, which is faster, and then you encrypt just the symmetric key by using public key encryption. Then in this way, you get the best of both worlds. You still achieve in public key encryption, but you do not need to use public key encryption to encrypt the whole bulky payload. So yes, we researched this idea and try to port it to searchable encryption. So you almost see the scheme already, but now let me just talk about the syntax first, and I will talk about some of the other challenges we want to tackle. So we still have a single reader and multiple writer, and we also have the cloud server. So for setup, the reader will just output a public secret master public key and master secret key pair through an algorithm called R setup. R stands for reader, obviously. And then the writer, they also have a simple W setup algorithm, and actually they will, after executing this algorithm, they will just output an initially empty DSSE instance. So each of the writer use this W setup algorithm. Afterward, it will output a DSSE instance, and then yes, the cloud server will just store all this initially empty encrypted database. and possibly some additional data structure, and that is our setup phase. Then how do we do the writing, or in SSE terminology, that's update. So any writer could output an update token U, like in DSSE. And for example, this writer they upload this U to the cloud server. Then likewise, the server will do the update by using this U to operate on this writer's encrypted database, the DSSE instance uploaded before. For example, like this one. And then for searching is also following the similar pattern you are expecting. So the reader will output a search token like S through a search token generation algorithm. The input will be the master secret key, the target keyword, and now one additional input is the set of target writer. So for example, for whatever reason, the reader just interested in every other writer or a particular writer, so he or she can also specify this piece of information in the search token generation algorithm. And the rest is conceptually straightforward as well. So reader upload this search token S, and then the server use this S over all this DSSE instance or the whole HSE instance as a whole to process the search through a search algorithm. Okay, so then of course afterward, eventually the reader can get back the corresponding file. So yes, that is the functionality.
Sorry, Sherman, I have a question. So in the definition, like it seems like that every writer is mapped one-to-one to its own DSSC instance. So does it mean that if a writer wants to update, it can only update its own instance and it cannot update the other instances of other writers? Is that true?
Yes, you can say so. Yeah.
Okay, thank you.
Okay, and so yes, actually, you may think that is like another feature we want to realize, and I will talk about future later. Okay, and on the other hand, I think in this scenario, you can see the writer related algorithm is W setup, and then this update. And the update, although I did not make it explicitly, so update is for here, that's still our original requirement. We don't want any synchronization with the reader. We don't want any secret distribution beforehand. So in that sense, that's still like a public key searchable encryption, which the writer can just do his or her own writing. So then on that means it is also sort of like you cannot really use this as a attack or vulnerability to attack or to write over some other DSSC instance. So yes, that is. So that's why I think about it a bit. So maybe that is something you cannot really get rid of if you just mandate the requirement to be like public key search encryption line. But I will try to get back to you on the special part.
Okay, thank you.
Okay, so any other question from others? So if no, then maybe when I talk about a little bit more, then the whole context will be even clearer. So after the syntax of functionality, that will be the security requirement. So we still shooting for a something like DSSE or PKSE. We have our semi-honest server, and for here, but now we have a potentially corrupted writer because we have multi-writers. But if you think about the DSSE definition, again, the writer is simply the reader, and that means by definition, this party is honest. So we don't have that concern in DSSE security formulation. For PKSE, you can, of course, there's multiple writers, but the writer create independent encrypted database in a sense. So if, for example, the writer just go corrupt, and if the server remains semi-honest, meaning the server will just follow the protocol, then there's no security implication at all because the damage will still be confined to his or her own DSSC instance. So there is no security implication. And yes, I'm suggesting that we need to have to think about a little bit more beyond just viewing the security definition from the established paradigm. So now that is the quick shipment for HSE security definition. So yes, we are still talking about security against semi-honest server and potential cooperator. We have our usual parameterized definition based on leakage function input. So we still have our usual setup leakage, just leakage, and update leakage, and now we have this co-option leakage. And on the other hand, while that is pretty standard in DSSE for at least the former kind of leakage, PKSE typically does not feature such kind of leakage analysis, but we are trying to do something PKSE like here. So in modeling the co-option of writer, we have an additional co-option oracle. And on the other hand, because we still have the leakage-based definition, so this will have an implication on the history of the execution of all HSE algorithm through all this oracle query. So we have this DSSE light shipment, which we still will start with the setup leakage. As long as you put the initially entered database online, then that is already that could be already leakage. So we capture that. And then as usual, the adversary just trigger different oracle, like update oracle, asking the server to update something. There may be corresponding leakage, and there's also corresponding history updated or appended to the initial just set up history, and then we have such oracle query, so we just keep appending the history, and eventually we have this correction oracle query, and then we also do the same thing. So that is just an example. Of course, in the actual definition, you can query all this in an adaptive manner. So then the history will just be updated accordingly. Okay, so in a nutshell, that is just one additional oracle and one additional implication on the history. And yes, the usual definition, so we define an HSE being secure, parameterized by this four kind of leakage input. When the adversary cannot distinguish between two sequence of query with respect to all this history or just a raw gel treatment with the same kind of leakage. So that is, on the other hand, that means the leakage here suffices to simulate the whole HSE execution, including the co-option of a writer. So talking about that, there are of course some trivial conditions you should exclude, and which I will get into later. But that is the parameterized definition. So, and for that part, I will first talk about the basic idea, and when we come to the forward private construction, then the security implication, that trivial condition I was talking about will be more apparent. So we start with this GHSE. G stands for generic construction. So that is like the baseline construction. And if you have been thinking about that, that may be already in your mind, but let me spell it out. So for here, this GHSE that is for n writers, n is a system parameter. So basically, that just combine DSSE or PKSE in the form of anonymous IBE in a hybrid encryption manner. So for here, I will just say there's an IBE instead of spelling out as PKSE or anonymous IBE. So the idea is still like the basic PKSE construction, you treat the identity in IBE as the keyword in GHSE. The out setup algorithm, the reader will just run IBE setup algorithm to initialize an IBE instance if we are going to support n writers. So there's IBE copy 1, IBE copy 2, and so on up to IBE n. For writer, they just run the DSSE setup algorithm to initialize a DSSE instance and upload it to the cloud. So that is the two setup algorithm. That's quite straightforward. And the update, there's a little bit more detail here. So firstly, let me define the terminology. So we call DSSE update token to be UT, DSSE search token to be ST. You will see in a minute why ST is relevant in update. So to prepare an update token, that means to try to write something. That is the following step. So let's say that is the ith writer, Armando's n writer. So the first step is to generate the update token through the DSSE update token generation algorithm together with the keyword S. So that is obvious for there is an update for a certain keyword. And for here, if that is the first ever update, that means the writer try to write about this keyword for the first time. So that is keyword based. So not like there is the very first writing. Well, I mean, the very first writing by definition is the very first writing for every keyword, but for a particular keyword, if the writer does not execute the update token generation algorithm before, then for this step, this writer will also generate the search token. The idea is just exactly like hybrid encryption. Because we are doing in a hybrid manner, we want to prepare the reader to have the power to search for things to be updated over this DSS instance. Hence, for this very first update for a particular keyword, the writer also prepared the search token ST. Then the rest is the ST, the search token will be encrypted under the IB instance set up by the reader, and then the UT will be just uploaded to the server along with the encrypted version of the ST. If there is the first one, then it will be sent to the server. Okay, so the regular UT, if that is the first update for a particular keyword, then we IB encrypt the ST. And the IB instance we are talking about is the IB instance. Okay, so then the update is just straightforward based on the structure. So So the server will try to use UT to work over DSSE instance of the IF writer through the update algorithm of the underlying DSSE scheme. And then the encrypted ST within the IB ciphertext will be just stored along with this DSSE database. So of course, the search will do something on that. So that will be the search algorithm. So for searching over a certain keyword W towards a writer subset S, that is a subset of the parser into N. So the search token will be working in the following way. So for each writer the reader want to search, then that the IF one, the reader will use the IB instance of the extraction algorithm to extract W's decryption key. So for example, there are two writer the reader want to search, and there will be two such execution and two such IB decryption key. Then the search will be the cloud server, upon receiving the IB decryption key, decrypt that IB ciphertext I mentioned in the last slide, get back the search token, and then you can use the search token to work over the DSSE instance of the corresponding writer. Okay, so yes, that is the hybrid searchable encryption spelled out. That's generic. You just use IB and DSSE as a black box. And now,
so I have a question, Sherman. Like, so correct me if I'm wrong, but it seems to me that during the updates, there is a phase where the writer needs to know whether what it's updating is the first time it's updating or not. So it seems like that the writer needs to be stateful in some sense. So is it the case, or is there something implicit that I didn't understand? Is there?
Yep, that is okay. That is required, and
okay.
And yes, that is required, and the justification for deploying this in practice, that's sort of like the outbox situation. But for here, you just simply mark a bit talking about have I ever write about this keyword before or not. So yes, that is required. So by definition, there is the information required for this step. So that's stateful.
So then does it mean the following? Does it mean that for every writer, it needs to keep a state that it's linear in the number of keywords that it has updated, which is kind of like similar to the normal dynamic searchable symmetric encryption, because usually under the hood, they all, in many cases, that they keep a linear state. It seems like it's the same thing.
Yep.
Okay.
True.
Okay. But also, like, it is worth maybe mentioning that this is where you are different from traditional public key searchable encryption, because like in that setting, writers are not stateful.
Yeah, correct.
Okay.
Yep, correct. Yeah, thanks for the notes. Yeah, and if we really want to get rid of the state, then yes, the obvious consequence will be it will affect the reader side efficiency. But yes, that is stateful. defense probability is up. So yeah, that is something worth putting explicitly. So if no further question, then yeah, I will try to discuss about the property of this generic scheme. Of course, we will try to do something better. That is why this slide we try to talk about why that is not ideal. So firstly, that is almost like we can achieve what we have for PKSE. At least there's no secret key distribution because certain secret key is not desirable for here. Yes, that's stable, but the writer only need to use the reader's public key to create an HSC cipher test. And yes, so that is also does not require synchronous communication. The writer can write independently. The writer does not need to talk to other writer. The writer does not need to talk to the reader beforehand because that is just generating the DSSC update token and the corresponding. I don't just the update token. And yes, so we are talking about we always have the trivial solution which somehow assume the writer will just coordinate with each other and then try to build the ciphertext nicely. So that rule out that part as well because of this requirement. Before I move on, so there is not like a property of this particular construction, but the property of like the paradigm in general. So after all, if we stick with these two requirements, that is still a public key-like scheme. So in that sense, we expect that we should be the corresponding public key operation to differentiate between their encrypted update. So that seems to be the baseline. There may be something we can think about to get rid of this paradigm, but at the moment, it seems to be quite reasonable to assume that. So with that, then that will be our search complexity. So you can see there are two terms happening. So we have our usual AW, meaning the number of update on the search, the keyword W. For this part, that can be symmetric key operation. But yes, as I just tried to set up the context here, so we have another additional term, which is the size of a certain set W, where W here means the active keyword written by the search subset. Okay, I will talk about this statement again. So for each search, you can confine it to a certain set of writer. We call it S. And then for here, because of the requirement or the observation here, we need to go through the active keyword, meaning that this set of writer has already written something about these keywords. So we need to go through this part, and that will be linear in this set size. And for this part, that will be based on public key operation. So that would be, and to be concrete, talking about our generic scheme, that will be the IBE decryption part we are talking about, which is using IBE decryption over all these IBE ciphertext to get back the search token. And that's why I say if the writer is not stable, then it will affect the search capacity. Okay, so we are almost there, and we try to say that is seems to be arguably inherent. Beyond that, there's an important property that's still missing. That is there's no bypassing at all because the DSSC search token. I did not talk about anything like refresh or things like that. The DSSC search token is by definition static, so we need to do something about that. So we achieved something already, but this would just require us to rethink about how do we construct the scheme better. Okay, so now I will move forward.
Sorry, Sherman, like I'm not sure like I understand very well like why in your search complexity you have the number of active keywords written by S instead of just having the set S, because that I mean, maybe what I'm missing is there like, are you assuming something about the IBE encoding of the keyword space here, or is it something else? Because here, if you look at the search algorithm, what you are doing, or maybe I'm missing something here. For all I in S, basically you have like S writers, like let's say like the number of like, let's say your set is composed of 100 writers. So you have 100 writers. And then for every writer, basically you are doing a decryption, an IBE decryption to recover the search token. So basically, like if I do, if I reason about this, it means that your search complexity, basically you need to do S number, like the cardinality of S operations plus AW, that you already have in the complexity. So what is the difference? Actually, I think what I'm missing is that what is the difference between the cardinality of S and capital W that you are writing?
Yeah, I guess I should spend more time on that instead of just using this succinct description. So actually, you are correct, and actually this set is larger than the set you're talking about. So for example, like Writer 1 has written about two keywords like A and B, and your Writer 2 you written about C. Then that will be the linear in A, B, and C. So we need to go through all this. And that is what I meant by so-called active keyword, because I am actively writing about on these two keywords. So yes, that is if everyone just work about a single keyword, then that's cardinality of S. But yes, there is more than that.
I see. So basically, like sorry, Sherman, just to repeat what you are saying. So basically, if you go to the previous slide in your search algorithm, basically when you have for I in S, the server runs IBE decryption over the I ciphertext. So basically this step is involving a linear search over over the active keywords in order to just decrypt and output just one search token that you will need. Okay. Okay, I see.
Yeah, correct.
Yeah. So which means that in the worst case, like sorry, like I'm just thinking maybe so which means that in the worst case, in this multi-writer setting, it means that let's say that I am a reader and I want to search over all of the DSSCs. It means that my search complexity will be still linear in the number of updates across all of the no, I see. No, I see. Like it's just the number of keywords. Okay, now makes sense. Okay, I got it. Yeah, makes sense.
And there will be something related for the better construction as well.
No, it does better than linear. Yeah, makes sense. Yeah.
So any other questions? So we will talk about the same thing, but it's more generalized version. So yes, that is this definition. So in case I write about a keyword A, even though the reader does not interest in keyword A, but because there is still PKSE's cipher test, so the cloud server need to go through each of these for the same writer. Then I discover a particular entry will be something I'm interested in. Then I proceed with the symmetric keyword. So this is like the additional overhead, not quite like the very optimal one, but yes, this is the additional overhead. But yes, we still have a bigger problem. So then with that, then we have one more rule. So we don't have forward privacy, and then we also have a problem I did not explicitly mention before. So the token size will be in terms of the cardinality of S, because they are just S writer you want to search, then this will be SIB decryption key to be dedicated to the account. So that is something we will, and also correspondingly, because we have the reader maintaining n instance of IB for n writers, so the reader storage, although there is not secret key storage, but the reader's secret key storage is also linear in this bigger n, so n is greater than the maximum of cardinality of S is n. Okay, so yes, we did that sublinear search. We also have controllable search, because for here, if I just want to search over one writer's database, then just one. But if I want to search for all n writer, that would be linear. So yes, that is the desirable part. Undesirable part we will tackle for the better instantiation. And by the way, also notice that we are still working under the assumption that there's no secret key distribution, no synchronous communication between the reader and writer, and that will be tricky to achieve our forward privacy, which I will tackle later. For now, I will quickly address this part of the table, that is the token size and the reader storage, and then I will spend more time for the forward privacy part. For this one, I try to introduce a primitive called key aggregate encryption. and then I extend it to something called ID coupling key aggregate encryption. So we have a regular set of algorithm as like a typical IBE scheme. We still have setup, keygen, and extraction for decryption key and then decryption. And let me try to talk about the basic so-called key aggregate encryption first. That's an additional feature which the extraction algorithm can try to produce a so-called aggregated key, or in another sense, this key will aggregate the decryption ability for a subset of class. So for here, notice that I'm still talking about an existing notion that is actually my co-author paper in a journal IEEE TPDS. So KAE, there is a notion of class which try to confine the decryption power. So likewise for encryption, you also encrypt specifying which class you want to encrypt to. You can encrypt to class 1, you can encrypt to class 2, or you can encrypt to class 1 and 2. So that is the concept of class that is different from identity. So that is the basic KAE. And when we try to couple this notion with identity, then we have the extended definition, which the ICKAE algorithm, the extraction algorithm, can just compute an aggregate key while this aggregated key is confined to a certain identity. If you think about the application in terms of the GHSE, that's almost like what we want to do to try to confine the searching power to a particular keyword, but we want to talk about any subset of the vector class. So yes, before I talk about this connection, then yes, for ICKAE, the power is like we can produce a constant size private key such that it will encapsulate the decryption power of the so-called class 1, class 2, and to class n. That can be any arbitrary subset. And the other part of the functionality or efficiency requirement is that the ciphertext, the aggregate key, I just spell it out, and the master secret key size are all independent of the number of classes. And that means, for example, if you want to support n classes, the ciphertext will still constant size instead of linear in n. For this, I already spell it out, so that should be constant size no matter which subset we are talking about. And the master secret key is also independent of the parameter n here. And in case you are familiar with broadcast encryption, so if you think about that, that is like the dual rules of broadcast encryption. For broadcast encryption, the ciphertext is constant size. We don't really specify the primary key size, but it's usually sublinear in the number of reader. And for here, there is the dual in the sense that I try to make the decryption key compact. No matter which subset we are talking about, in broadcast encryption, I try to encrypt to a subset of them. I try to delegate the decryption power for a subset of them. And that piece of information, that is what we call aggregate key, that will be constant size. So that's a little detour in case you are familiar with broadcast encryption, but back to our story, the identity part is will be the keyword in searchable encryption. So yes, we also expect this scheme to be anonymized in the sense of identity anonymous. And when being used in our hybrid searchable encryption, the correspondent will be each writer will belong to a class. So that is how we try to get a better instantiation of our GNet scheme. So to spell it out, that means if I try to use this new primitive to replace n instead of IBE, then we will have order 1 token size, order 1 meter storage, and that is what we want to get rid of in terms of these two red boxes in this table. So there's order 1, no matter which subset I want to search about, there's still order 1 size. And yes, that will be something talking about the ICKE instantiation detail. One thing I want to highlight is that that is a pretty efficient scheme. It only requires 2 pairing, arguably the optimal one. That is in random oracle model that's based on some dynamic assumption, those Q-type assumption. And actually, there's a little caveat, but that will be a little bit complicated to talk about. But on the other hand, that is what we achieved, and that caveat can actually get removed with 1 more pairing, but that's beyond the scope of the current paper. So yes, module, the underlying detail that we have this new pairing construction of ICKE. which just replace n instance with IBE, and we can upgrade HSE into for instance. Okay, so that is the more part on the number theory detail, which I omitted. But if you are interested, I can talk about it more. And now, the more SSE favor problem, so the forward privacy. So let me quickly recap the traditional forward privacy definition. So obviously, I will try to twist a little bit because we are working under the requirement of there's no secret key distribution, there's no synchronous communication. The idea of forward privacy, you can try to summarize in the for instance, the delegated search token cannot work for any future update. So for example, the token are issued in the foreign sequence, we have the update token UT1, then we issue the search token, so the search token can search over this document. Then the sequence goes on UT2 and ST2, so that's still confined in this way. And then, so that is how we try to argue about forward privacy, or that is the forward privacy notion we want to capture. So the old search token always confined to the update happened before it. It cannot work for any future update. So for here, this token cannot really identify UT4 that happened afterward. Okay, so that should be the basis for this audience. And now towards the newer notion. Then there is a little bit of the history of the literature I want to talk about. So the first definition, formal definition by Boss, his idea is trying to capture the following. So his definition, if we talk about the update being a keyword file tuple W and F, so his idea is that the leakage of the update operation will leak nothing about the keyword. On the other hand, he does not really specify about F, so leakage of F, the actual file is acceptable. And in another work with another of my former student, virtual guy, so we consider slightly different. So we tolerate the partial leakage of the QAW, but on the other hand, hiding F will be an option. So obviously, if you just leak about everything, there's no forward privacy at all. That is a non-interesting way to achieve forward privacy. But if we try to hide one of the end of this WF relation, so arguably that is still we can still achieve this original spirit. The delegated search token cannot really work for any future update if there is some partial leakage of W. Of course, that all depends on the definition of what does this partial leakage. And then for this, I will use this definition for this talk. So I consider this related definition sort of combine both. So the update function is in the following form. We have L prime and L prime, our usual stateless function. L prime in F, so that is leaking. Leaking F is an acceptable option, and here is the partial leakage. So what this complicated notation means, it means it try to read the update history, and we try to have the current timestamp of the execution of the SE scheme. So in case U is, I should have removed that. So U is the timestamp. Just think about, just forget what this at the moment. This is based on W, whether there's a null set. It simply means a single bit indicating whether that keyword W has been updated before. So whether someone has written about this W or not. So this simple leakage. Yes, that means if you can see the correspondent, that is like the writer stage, so the writer need to keep track of whether he or she has written some about W before, and that is the leakage we are shooting for. Okay. So that is a twist or the baseline definition we will be working with. And then, yes, as mentioned, we usually require a refresh of the database or the state after each search. That is the traditional approach to achieve forward privacy. But that is not applicable to multi-writer setting because the writer will have no idea when the reader will issue a search query. So in SSE, reader is the writer. After reader try to search, then the refresh, that's total in the total control of the reader. And on the other hand, for here, in the multi-writer setting, the writer does not know what is the reader up to. So the writer, for example, does not know which keyword the reader has just searched for. So that is not coordinated, and that's why I emphasize there's no synchronous communication before. And that is making us difficult to achieve any form of to achieve the traditional form of privacy, even we try to relax in this way. And so that means I'm trying to argue that we need some new idea because traditionally everything is done by the reader, but now the writer also need to take a part. And now our way out is to try to introduce the notion of epoch or an epoch-based timeline. That is like you may have heard about in other occasions. For example, when we talk about forward secrecy in public key encryption, so we consider the system timeline as a set of timestamp. So like 0, 1, 2 up to 3, that is also our like typical timestamp in DSSC leakage formulation. We try to assign a self timestamp to a certain epoch, like E1, E2, and so on. So yes, there's need to be synchronized, but there's a loosely synchronized clock. So as long as we are up to the granularity of the epoch, that's okay. So we assume there's a global clock which the reader and writer and the server and the account server has access, saying that, for example, now is the 4th epoch. So with that, then we will formulate a variant notion called epoch-based forward privacy, which is actually joining the idea from forward private public key or even private key encryption. So we still want to capture the essence of forward privacy. As I argued before, the search token cannot retrieve update at future epoch. So yes, now I changed this terminology from just the general sequence to epoch-based, so the granularity is up to the epoch. So let me spell it out with an example. So we still have almost the same example, but just replace the terminology. So in epoch 1, we have the update 1. Then after that, there's a search token issued, so the search token can just search over this UT1. And for example, in epoch 2, there one update or UT2, search token has been delegated, and now there's another update in the same epoch. So for this reverse definition, this search token, instead of just trying to search backward, because this search token is supposed to work for epoch 2 as well, so both of these updates can be reachable by using this search token. So that is the difference. Then yes, the epoch just goes on, and then we have also another sequence, another epoch, another search, that the search token is the first thing the reader issued at this epoch, but yes, it can also search for update happen later while still within the same epoch. Okay, so any question on this one? So then, yes, this common epoch information will serve as an indicator for reflection, which is our hurdle I tried to argue before. The writer does not know what the reader is up to, but now they can always refer to this loosely synchronized clock given the current epoch information. So in that sense, that is like the thing which try to unlock the possibility of achieving some form of privacy for in the multi-writer setting. With that, then let me spell out the more formal definition that is just combine things together. So we consider a DSSE is epoch-based forward private. If for all the keyword file tuple W and F, and being updated at epoch E is the current epoch, and we also require that W is not being searched at this epoch or before. So because in the leakage we use timestamp U, so that's the correspondence between the timestamp and epoch. And you still see the same definition, so that is the only thing leak about W is whether it has been updated before at all. And when this definition is being applied to HSE, obviously it will further require that the writer who issued the corresponding update query is not corrupt, and that was the trivial condition I was talking about. So if you think about that, the writer, I obviously wrote this before, and you cannot really fool me with all these things. So that's the trivial condition we need to exclude. So otherwise, we just confine this, and by formal argument, this also sort of capture the essence of forward privacy, but we loosen this a little bit in this sense. Okay. So then I will just quickly go over the construction idea because time is limited. The idea is we try to update the. So firstly, I need to construct the underlying DSS scheme, which achieve this kind of airport-based FOIA privacy. Then naturally, I will use this to replace the DSSC in the GA construction. So the idea of this construction will be I try to retrieve the update of the same airports as normal DSSC, but on the other hand, we try to also maintain this search token for per airport. So I store the per search token with the first update per airport. So for example, that is the actual update I want to do, but I try to prepare before in the sense that so for all this update which happened in the second airport, I try to also put this search token for the previous airport as like my very first update and so on and so forth. And yes, I'll echo to terrace observation, so that is sort of like trying to have the waiter stay requirement for most DSSE, for most common FOIA private DSSE manifest in this room. So I have asked and for this one, that is also for efficient concern. So for the construction idea, we try to append this search token for high app. Any question at this point? Okay, so then there is a lot. So I am just talking about the general idea of Apple. If you want to be more generalizing, you will discover there's another tunable parameter. So in case you want to confine it to, for example, if you just consider an infinite small airport that is just our regular definition, then we have the regular notion of FOIA privacy. Or on the other hand, that's all about temporal delegation. So we can achieve some sort of temporary delegation for this airport concept. So a shorter airport trade flexibility for higher FOIA privacy. And on the other hand, yes, to the other extreme, if you consider an infinitely long airport that is just like everything is searchable, there's no FOIA privacy at all. Okay, so with that, I'm almost there. So there's for a private HSE, less instantiation, we call it FPHSE. So I try to instantiate the GA construction with our upgraded airport-based FOIA private DSSE and that identity component key aggregate encryption. So it will inherit the order one token size and reader storage from ICKAE. That's because we also talk about airports, so that will also be independent of the time period length and also our regular feature independent of the subset size we are trying to do for the controllable search. It retains FOIA privacy from the EDSSE as well in the multi-vector setting, or it is that single bit whether this .bu keyword has been searched at current airport or not. Okay, so we are almost there. On the other hand, there's also one last issue. Because we try to introduce things like this, we try to introduce that extra search token thing. So that will just slow down the reader searching time if this kind of search token keep accumulating across the airport. Because for now, we have the airport going forward. The waiter need to also prepare this search token just like in this slide. So eventually it will accumulate a lot. So our way out is actually the idea called partial reveal, which happened in the SSE context for other purpose before. So in this sense, in a nutshell, that is the waiter will try to actively try to do some update about the ICKE encrypted token, which replace the regular IB token in the GA construction for a new airport. So basically, in a nutshell, the idea is just like because the waiter knows about all this thing has been still there, so the waiter try to do something more to like rebuild this path to encrypted database. So that is the high-level idea. The MC detail will be in the paper. Let me try to highlight some of the features. There will be low impact on security as long as because the new token still remain encrypted. And actually, the waiter still need not to be synchronized. They could go offline for a few airports without harming security. When they just go online, they can choose to do this partial rebuild over their own DSSE instance. There's no obligation. In that sense, they will retain the underlying search, the basic GHSE, the generic one search time. So that all depend on the rebuild capacity. So I will just show it by experiment that is acceptable. So that is like the last piece of idea. I need to have everything worked out nicely. So in a nutshell, that is our new construction for a private hybrid searchable encryption that's based on epoch-based for a private DSSC plus the ID coupling key aggregate encryption plus this partial rebuild technique. Okay, so that is like the design part. Then to wrap it up, that is, yes, we have everything nicely tinted or being green. So for privacy, controllable search, sublinear search, order one token size, order one meter storage. And now the very last part is I will quickly highlight some of the experimental figure. So because we are motivated by this kind of application like EHR, sensor, and our regular email writing scenario, so that is the data set we are doing with. Then yes, the building time, because we just add a little bit overhead, only everything else is almost like symmetric key encryption. So if you try to compare it with the regular public key searchable encryption or that SPCHS construction, which is heavily public key based, then we see order of magnitude improvement for the building time. And that is based on this data set. So the average rebuild time for write per writer will be at most 2 seconds. And that is how we argue. We think that there is the rebuild time being acceptable. And yes, the more detail about the actual experimental setup is in the paper. And by the way, for the generic one, that is of course even faster because that is not for private, but and if we want to care about privacy, then we need to pay a little bit overhead. There is our second construction, and these two are the existing one. And yes, order of magnitude being faster. So one more slide about the actual search performance, our very original motivation, motivate the whole thing. So we try to vary the subset size. That means the subset of writer we want to search over for this particular search. In general, if you try to include more writer, then of course it will affect their collective database size, their result size, and the active keyword also go accordingly. And for here, I just highlight one facet of the experiment, and you can see that it's still going slowly in this order of magnitude, and that is our usual relative comparison. Actually, no, sorry, I take it back. So that's not our usual comparison. So the last tool, the fastest tool is of course our proposal, but because we try to use that order one thing, so for this case, because we have the order one feature, that is the order one key size capturing everything. So in this, okay, so in this case, yeah, so we are almost getting there, but there is the little overhead we want to place over that additional feature of order one size key. So that, sorry, actually I was right. So there is basically two proposals. The generic one with no forward privacy is still the fastest, but there's no forward privacy. But on the other hand, this one is a little bit slower, and then there's order of magnitude better than the other one. Okay, and yes, Sherman is the one who did the hardware for this as well, and he will know more about that. Okay, so now our concluding slide. So what we have done in this work, so we defined the leakage-based security definition with coordinate writer. We try to argue that there's non-trivial combination of existing paradigm because there are recent features in the existing one. We propose the notion of ID coupling key aggregate encryption. It may contribute to the set of so-called cloud cryptographic technique for having some access control with search power, because we sort of inherent the nice feature for IBE, but we have this key aggregator feature added. We also proposed the notion and construction of epoch-based for private symmetric searchable encryption. There is a new formulation providing a tunable treatment for privacy. We also introduced that partial rebuild technique, which I just quickly went over with an overview for maintaining privacy while also maintaining search efficiency. And yes, our building block can be of independent interest, and we propose generic construction and concrete construction for this highly searchable encryption idea. And then yes, we perform some experiment to validate the deployment performance. That is all we have done. So Then yes, by this point, I hope you'll get the sense of why I try to title the paper in this way. So all of the writer trying to help the reader to maintain this database to have a more efficient construction. Namely, we have sublinear search, we also have FOIA piracy, and we also have the controllable search feature. So for this, I conclude this talk and I welcome any further Q&A.
Thank you, Sherman, for the
Thank
talk.
you.
Yeah, it is really interesting. There is definitely like a lot to talk about. Like I feel like that this talk may have easily been like more than 1 hour just to appreciate all of the components. It's really nice. So yeah,
Thank you.
yeah. So we are already over time. So maybe we can get like a couple of questions from the audience. And
yeah, I had a
yeah.
question. So yeah, I really like the construction and especially the modularity is very nice. And so this was making me wonder. So if you replace or you know the way you presented it was with a kind of a standard DSSC scheme that handles, I guess, like regular keyword search. If you replace that with a scheme that handles like Boolean or other kinds of expressiveness, does everything kind of still work? Or
Yeah. I think it should work.
okay.
And yeah, because you just try to or thinking this way, all the house server need to do is just to go over all these public key searchable tests. And then you unlock it and then you use that search token for everything.
Right.
And actually, that is like the old story. So if you still remember when I was still your intern, I talked about this after reading your structured encryption paper. So that's where I got the inspiration. But then things are not that fancy, so I just stick with the basic construction. But now things got fancier and all this confidence requirement make a case here.
Nice.
So yes, so that's all about just like your structured encryption ideas, so all about what that token bit encrypted can do. So if you try to extend it with DSSC with fancier feature, for functionality it should work. For security, then it depends.
Right. Okay. That's great. Thanks.
So I have like another question, which is like I was thinking. So one thing that makes like public key searchable encryption a little bit hard to deploy, of course, there is the linearity component of the search, but there is also of what we call, or what I call, like dictionary attack, or whatever we will call them in is that if you are a writer, you can always like add dummy or whatever keywords you want to add, and then wait to get like at least in the PEX paper to receive the trapdoor, and there what writer has written at any point in time, and that mapping, which is like really easy to do in the public setting. So in your case, like it seems like that this still persists in some sense, because let's say that I am a writer and I am colluding with the server, and I just like update dummy stuff, like just keywords, like all of the dictionary, let's say, like that I can think about. And then I will just sit and see whenever I am part of that set S in the search, I will just see if the other writers, they have made an update for whatever keyword that I have already inserted. So this dictionary attack still applies in some sense. So is this true, or am I missing something?
Yeah, you're correct. So because we are still trying to do a public key search by encryption, like, so yes, that is still an inhuman weakness.
Okay.
And that goes to my next word.